Hi, this is Sarpasha, and today we are going to learn how to figure out the SI base units of different derived quantities. But before we move on towards finding the SI base units of derived quantities, we need to first know about the 7 base quantities and their units. So here you can see finding SI base units of derived quantities. So we have a total of 7 base quantities. Number 1 is length, number 2 is mass, number 3 is time, number 4 is current, number 5 is temperature, number 6 is mole, and number 7 is luminous intensity. The order doesn't matter. You can write any one of them in the beginning or later. That is not an issue. Now let us talk about their base units. So if I talk about length is measured in meters. The SI base unit is meter, and it is symbolically represented with a small m. Mass, the SI base unit of mass is kilograms, and it is measured in kg, small k, small g. Time is measured in seconds, and it is symbolically represented with a small s. Current is measured in ampere and symbolically represented with capital A. Temperature is measured in Kelvin, and the symbolic representation is capital K. Mole is calculated obviously in mole, and you can write MOL as its base unit or the symbol of the base unit. Luminous intensity is measured in candela, and that is measured in CD. Right. So we will be focusing less on the last two, this mole and the luminous intensity, but the first 5, length, mass, time, current, and temperature, they are going to be very crucial. They are going to be very important in the upcoming. Now once you know these 7 base quantities along with their units and the symbols of their unit, please remember that these SI base units or the symbols of the SI base units are case sensitive. That is, seconds is small s, you cannot write capital S. Kilograms is kg, that's a small k and a small g. You cannot write capital K and G, otherwise someone would have read it as Kelvin gram. So kg is a small k, a small g. Ampere is capital A, so you cannot write a small a for amperes. So please remember, these are case sensitive. If an alphabet is in uppercase, that is, if it is capital letter, you need to keep it in capital letter. If I have written it in small letters, you need to ensure that you always write it in small letters. Now moving on, before I start solving any question, there are basic rules while doing the base units or while figuring out the SI base units. Now let us go through them one by one. Now the first rule is that SI base units cannot be added or subtracted by usual arithmetic or usual algebraic rules. Now what does it mean? For example, if I write meters plus meters plus meters, in basic algebra that would have been 3 meters, but while figuring out the SI base unit, this is going to be meters. If I have, for example, kilogram per second minus kilogram per second, by basic algebra this has to be 0, but while figuring out the basic SI unit, kilogram upon second minus kilogram over second is kilogram over seconds. When we will do such question, you will realize why, what is the significance of this, but you should remember the very first rule, that SI base unit cannot be added or subtracted by usual algebraic rules. Now the second important point is that the SI base units can be multiplied and divided by basic algebraic rules. For example, if I multiply meters with meters, the answer is meter square. Similarly, if I have an equation like kilograms multiplied by meters per second square multiplied by seconds per kilogram square, so I will simplify it by using basic algebraic rule. That is, this kilogram will cancel this square and this square will cancel this second, and I will be left with meters per seconds per kilogram. So The first rule was that SI base unit cannot be added or subtracted by usual algebraic rules, and the second rule is that SI base units can be multiplied and divided by basic algebraic rules. And now the next point is that constant number in an equation has no SI base unit. Now when I say constant number in an equation has no SI base unit, I mean if in an equation you find pi, you find 3 upon 2, you find 1 upon 6, etc., anything like this, so you are going to ignore that constant number. So these three basic rules. The first rule is that the SI base units cannot be added or subtracted, then they can be multiplied and divided, and then the third important thing is that a constant number has no SI base unit. Now probably you must be wondering what are these rules and why are these rules. Probably when we will start solving question, we will realize the significance of these points. So now it's time to solve some questions and see how these basic rules of SI base units will help us to figure out the SI base units of different derived quantities. So I'm going to start off with area. So if you want to figure out the base unit of area, you need to know the formula of area. So for example, if I'm assuming a rectangle, the area of a rectangle is given by length into breadth. Now length is a length, so that is measured in meters. Breadth is also a length, that is also measured in meters. So meters times meters, because base units can be multiplied, this is meters square. So this is how I will get the SI base unit of area. But if someone says that I have a circle, and for a circle the formula for area is pi r square, it doesn't matter. Not a big deal. You can use this equation. You will eventually end up with the same answer. Now, while figuring out the area, one thing you need to remember is the third important point. That is, if I show you the third point again, constant number in an equation has no SI base unit. So what I'm going to do here is that while figuring out the area for a circle, I will ignore pi. I will ignore pi while figuring out the base unit. Why? Because pi is a constant number, so I'll ignore pi, and in place of r I will write meters, because r is a radius, radius is a length, and because I have a square here, so I will put a square, and this is how I will get the base unit of area, which is again meters square. Now let us try to do another example. That is volume. Now we all know that, for example, if I have a cuboid, the volume of a cuboid is given by length into breadth into height. Now length is measured in meters, breadth is also a length, that will be measured in meters, height is also a length, that will be measured in meters. So meters times meters times meters, that will be meter cube. So the SI base unit of volume is meter cube. Similarly, if someone says that I have a sphere, now we all know that the volume of a sphere is given by 4 over 3 pi r cube. Now again, third point is very important of base units, that is 4 upon 3 pi. This is again a constant number, and this constant number in an equation has no SI base unit. So I will write nothing in place of 4 upon 3 pi r cube, but in place of radius I will write meters, and because it has a power 3, so I will write power 3 here, and that will be meter cube. Alright, so now let's take another example. This time I will be discussing density. Now we all know that density is mass over volume. So if I talk to you about density, so let's say if I represent density with rho, that is going to be mass over volume. Now mass is measured in kilograms, as I have already explained you in the beginning of this lecture. Volume is measured in meter cube, we just figured out, and now you can see that the SI base unit of density is kilograms per meter cube. Now again, in order to figure out the base unit of any physical quantity, you should know what? You should know the formula of that physical quantity. So if I'm going to figure out the base unit of speed, I should know that speed is given as distance over time. Now distance is a length, and that will be measured in meters per second. So the SI base unit of speed is meters per second. Now this can also be written as like this, because this seconds was in denominator, so if I bring that in numerator, that would be second power minus 1. That's not a big deal. So this is the SI base unit of speed, and the same will be for velocity. Why? Because again, velocity is displacement upon time. Displacement is also measured in meters, so it doesn't matter if it is speed or velocity, the SI base unit is same, that is meters per second. Let's take another example, which is of acceleration. Now if I talk about acceleration, again I should know the formula of acceleration, which is v minus u over t, change in velocity over time taken. Now v is final velocity, u is initial velocity, and time, t is time. Now it doesn't matter if it is final velocity or initial velocity. As long as it is linear velocity, it will be measured in meters per second. So for final velocity, I will write meters per second, minus for initial velocity, I will write meters per second, whole divided by, for time, I will write seconds as it is. Now if I apply the basic algebraic rule, that will be meters per second minus meters per second equals 0 over seconds, which would be 0. But this is wrong. Why? Because you have to recall our very first rule of SI base unit, that is, SI base units cannot be added or subtracted by usual algebraic rule. That is, meters plus meters is meters. Kilogram per second minus kilogram per second is kilogram per second. Similarly, in our example here, meters per second minus meters per second is not 0, but meters per second minus meters per second is meters per second. So let me correct it for you. So this is meters per seconds over meters per seconds, and that becomes meters per second square. And you can also write it as meters per second power minus 2. So they both are the same thing. Now after doing acceleration, I can move on towards force. Again, if I want to figure out the SI base unit of force on any physical quantity, I first should know the formula of that physical quantity. So if I'm talking about force, there are numerous ways to explain force, but the very basic way is, we all know, that is a conclusion of Newton's second law of motion, F equals ma. That is, force is mass times acceleration. So I know that mass is measured in kilograms and acceleration is measured in meters per second square. So I can say that the SI base unit of force is kilograms meters per second square, or I can also write this is kilogram meters second power minus 2. Moving on to the next example, that is kinetic energy. Now again, in order to figure out the SI base unit of kinetic energy, I should know the formula of kinetic energy, and kinetic energy is represented by 1 upon 2 mv square. Now again, 1 upon 2 is a constant number. Our rule number 3, that is, constant number has no SI base unit. So I will ignore 1 upon 2. M is mass, and mass is measured in kilograms. V is speed, and speed is measured in meters per second. But since I have a square over here, so I will put a square, and that will be kilogram meter square per second square. Moving on to the next example, that is potential energy. Now potential energy is given as mgh, which is relative potential energy. Now m is mass, and mass is measured in kilograms. G is gravitational acceleration, and that is measured in meters per second square. Again, because that is linear acceleration, it doesn't matter what acceleration it is. As long as it is linear, that is going to be measured in meters per second square. H is height, and height is measured in meters. So again, simplifying it, I will get kilogram meter square per second square. Move on towards the next example, which is work. Now we all know that work is a product of force and displacement in the direction of the force. So we have just figured out the SI base unit of force. Let me show you that. And yes, here you can see we have just figured out the SI base unit of force, which is kilogram meters per second square. So here I am not going to do the same working again. I am just going to write kilograms meters per second square in place of this force F, and now D is distance, which is length, that will be measured in meters. So again, the SI base unit is kilogram meter square per second square. It is interesting to note that the SI base unit of kinetic energy, potential energy and work is same, and they should be same. Why? Because if you remember in O levels, you must have heard that the SI base unit of kinetic energy is joules, potential energy is joule, work is also joules. Actually, we say that the SI base unit of joules, or you can say joules, is equal to kilogram meter square per second square. And this is the reason why we can add, subtract, because physical quantities with same base units can be added or subtracted. But it is not in every case. We will see where we can add or subtract. But you must have heard about kinetic energy minus potential energy is work done, and in a number of cases you must see potential energy getting added or subtracted to get the work done. The reason why is that they have the same base units, so yes, they can be added, they can be subtracted. Now the next example, which is movement, which is turning effect of a force. Now we all know that movement is again F into D. It is again the force, it is again the product of force and displacement, but this time this displacement is movement arm, which is the perpendicular distance from the pivot to the force. But right now I will not go into the detail of what movement is, because right now I am just focusing on figuring out the SI base units. So F, force, is again kilogram meters per second square, we just did in the previous example, and displacement is meters. Now that becomes kilograms meter square per second square. Now this has the same SI base unit as that of energy that we have just done. You can see for all the energies we also had the same kilogram meter square per second square. Movement also has the same SI base unit, but obviously they are not the physical quantities of the same nature, because potential energy is a scalar, all types of energies are scalar, work is a scalar, but movement, turning effect of a force, torque, they are all vector quantities. So they are different in nature. We cannot add or subtract movement or energy with each other. We will see that in the advanced physics when we will be discussing these topics in detail particularly. Now the 11th example that we have is of pressure. For pressure, again we need to know the equation of pressure. Pressure is force per unit area. In the previous examples we have already seen that force is kilogram meters per second square, whereas area is meter square. This meter and this square will get cancelled, and I will be left with kilograms per meters per second square. But there is another equation for pressure, and that equation is pressure due to liquid, which is rho g h. Now let us check out if this equation also gives us the same SI base unit. Now rho is density. Density is measured in kilograms per meter cube. We have seen it previously. G is gravitational acceleration, measured in meters per second square. Height is measured in meters. Now what I will get here again is this meter, and meter will make meter square, and it will be cancelled with this meter cube, and again I will be left with kilogram per meter per second square. Now what we need to understand is that for every equation of pressure, it doesn't matter whatever the equation is, if it is an equation of pressure, it should end up with an SI base unit of kilogram per meter per second. And now the next example is heat capacity. Heat capacity, which is symbolically represented by capital C, is equal to Q over delta T, where Q is the amount of heat energy that you provide to the system and delta T is the change in temperature. Alright? Now, it doesn't matter if it is heat energy, kinetic energy, potential energy, or whatever is the form of energy, chemical energy, whatever it is. If it is energy, the SI base unit has to be kilogram meter square per second square. Let me give you the example that we have just saw previously. You can see for kinetic energy, kilogram meter square per second square. For potential energy, kilogram meter square per second square. For work, kilogram meter square per second square. So even here for heat energy, while figuring out the base unit of heat capacity, I will be again using the same kilogram meter square per second square as the SI base unit of this heat energy. The change in temperature is final temperature minus initial temperature, which is T2 minus T1. Now that is going to be Kelvin minus Kelvin, which is again going to be Kelvin. So the SI base unit of temperature is Kelvin, and change of temperature is always Kelvin, because that is Kelvin minus Kelvin, which will give you Kelvin. Now please never ever cancel these two K, because you should know that this K is kilo and this is Kelvin, so they are not going to cancel out each other. Rather, my final answer is going to be kilogram meter square per Kelvin per second square. So this is the SI base unit of heat capacity. And now the next example is of a specific heat capacity. Specific heat capacity is symbolically represented by small c, which is capital C over m. That is heat capacity over mass, or heat capacity per unit mass. Now heat capacity that we have just saw was Q over delta T, mass as it is. So I will have C as Q over m delta T. Now all I need to do is to just put the values, is to just put the base units of every physical quantity and simplify to get the base unit of a specific heat capacity. Now Q is energy, that is measured in kilograms meters per second square, divided by this mass m is measured in kilograms. Delta T is change in temperature, which is measured in Kelvin. Now these 2 kilograms will cancel each other, and I will be left with meters per second square per Kelvin. Now the next example is latent heat of fusion. Now what is latent heat of fusion? Latent heat of fusion is nothing but the amount of energy required to convert a solid into liquid at a constant temperature. So this is nothing but energy. So this latent heat of fusion will have the same, it will have the same SI base unit as energy. So if latent heat of fusion is usually LF, or whatever is the base unit, is the symbol, its base unit is again going to be kilogram meter square per second square, which is the SI base unit of energy. Similarly, for latent heat of vaporization, the idea is different, that in latent heat of vaporization, it is the amount of energy required to convert a liquid into gas at a constant temperature. But again, the point is that that latent heat of vaporization is again nothing but energy. So it will again have the same SI base unit as that of energy. So again, even for latent heat of fusion or for latent heat of vaporization, the SI base unit is kilogram meter square per second square. Now the next example is a specific latent heat of vaporization. Now when you add the term specific to any of the physical quantity. The specific means nothing but divided by mass. That is, now we are measuring that quantity per unit mass for 1 kilograms. So now if previously we saw that the latent heat of vaporization, is kilogram meter square per second square is energy. So what is going to happen is that the specific latent heat of vaporization is going to be heat of vaporization divided by mass. Now heat of vaporization is measured in kilogram meter square per second square and mass is measured in kilograms. So these 2 kilograms will cancel out each other and I'll be left with meter square per second square, or you can write meter square second power minus 2, and this is what is the SI base unit of latent heat of vaporization. I will not be doing a specific latent heat of fusion, because that again will come up with the same answer. Now the next example is power, and we all know that power is work done over time, and we have previously seen that work is again the conversion of energy, and it has the same SI base unit as energy. We have figured out work in previous cases again as kilogram meter square per second square. So in place of work I will be writing kilogram meter square per second square, and in place of time I will be writing seconds, and I will end up with kilograms meter square per second cube. So this is the SI base unit of power. Now the next example is charge. Now charge is nothing. I know this is, when I say charge I mean electric charge, and that is Q, which is equal to the current times time. So if I multiply current with time, you remember I is Q over T, because current is the rate of flow of charge. So Q is charge, T is time. So if I make Q as the subject, I will get current into time. So current is measured in amperes, which is A, and time is measured in seconds. So the SI base unit of charge is ampere seconds. Now the next example is voltage or potential difference or EMF. Now, though there is a difference in potential difference and EMF, but the difference is just of the perspective. Otherwise the formula is same and the SI base unit is same, so there will be same SI base unit of voltage, potential difference or EMF. Now for that, again, in order to figure out the SI base unit of voltage, I need to know the formula of voltage, and that is work done per unit charge. Now previously we have seen that the SI base unit of work done is kilogram meter square per second square, and the SI base unit of charge is amperes seconds. Now if I simplify this, I will get what? I will get kilogram meter square per ampere per second power 3. Now this is how I get the SI base unit of what? Of voltage. But there is another way I can figure out the SI base unit of voltage, and I would want to try that new way. You see, we all know that power is voltage times current. So with the help of this equation, I can say that voltage is power over current. Now we have just seen that the SI base unit of power is kilogram meter square per second power 3. So if I use this kilogram meter square per second power 3 as the SI base unit of power, this is going to be kilogram meter square per second power 3, and current as ampere, then again I will end up with the same SI base unit, which is kilogram meter square per ampere per second power 3. Alright. Now the next example is electrical resistance that we measure in ohms. But again, ohms is not the SI base unit. The SI base unit has to be in kilogram, meter, second, amperes, and so on. So figuring out the electrical resistance, the SI base unit of electrical resistance, I can use the equation which is which is the conclusion of Ohm's law, that is V equal IR. So I can say R is V over I, which is voltage over current. Now we have just figured out the SI base unit of voltage here, which is kilograms meter square per ampere per second power 3, and current is measured in amperes. So this gets kilograms meter square per ampere square per second power 3. Now these 19 examples that I have shared with you till now, you see that these are the foundations. This will form the basics of finding the SI base units. But the game doesn't end here. Now what I expect from you is that before you watch the next lecture, you should practice a lot about these. I mean, you should practice again and again figuring out the SI base units of these physical quantities that I have taught you. And if you have any question, just feel free to ask me, and then we will see an advanced version of finding the SI base unit and seeing how these SI base units will help us figuring out the homogeneity of an equation and a lot more. So this topic is not over yet. We have a lot to come after this lecture. I hope you enjoyed this. Practice as much as possible, because the greater the practice, the easier will be for you for the upcoming challenging questions of this topic. Thank you very much.